Today we are going to talk about amino acids and how to identify them. Okay, so we have our hydrophobic amino acids, we have our polar amino acids, and we have our charged amino acids. The first thing that you need to do is identify what the backbone is. And the backbone is going to be the same for each of the amino acids. So that's the non-highlighted part here, okay? And so I look for it with the COO negative and the NH3 plus, okay? Again, it's the same. Those are important in, figuring out how things interact with each other as well. But what's really important are these side arms, okay, or these variable groups. So our hydrophobic amino acids, this is my silliest story. So we have carbons and hydrogens. They're like just normal kids on the playground that are trying to eat their lunch. They're scared of the water because they're hydrophobic, so they're hiding on the inside, okay? Carbons and hydrogens. Whenever you see this ring, that's just carbons and hydrogens. Remember that carbons have 4 areas to bond, and so wherever you have a free area, that's going to be bound to a hydrogen, okay? So again, hydrophobic, just the carbons and the hydrogens. Then you have your polar amino acids, and these guys are our bullies. You have our oxygens, our nitrogens, and our sulfurs, okay? These guys are trying to steal the lunch money from the weaklings, the hydrophobic guys, right? And so if you look at the structure of water, okay, it's H2O, right? And why it's in a V shape is because the oxygen is trying to pull the charge towards it, which makes him polar, okay? And I think of it, polar bears like water, so they're hydrophilic. Polar amino acids are hydrophilic. And again, you're gonna see the very end be oxygen, nitrogen, or again, your sulfur. Then our final is that we have our charged amino acids. These guys are the ones that succeeded in stealing the lunch money. So they get to say that they have a negative charge or a positive charge because they actually stole that charge, okay? So then we look at our summary chart here. Okay, so we have our carbons and hydrogens. Again, these are hydrophobic, non-polar. And then these hydrophobic interactions, these have a huge impact on them, okay? Because this is going to be, they're scared of water, so they're hiding on the inside, okay? The bond strength, it's weak, okay? This means that only a little bit of heat will break them apart, and this will lead to aggregation, which is a fancy word for clumping, okay? Then you have our, let's go to our polar next, our oxygens, nitrogens, and sulfurs. These are divided into 2 because remember our sulfur is our ultimate bully. These guys are both polar. They have hydrogen bonds for the oxygen and nitrogen, and then they have moderately weak pH and salt that can break this bond. With the disulfide bonds, di means 2, sulfide means there's 2 sulfurs. This is really strong. This is a covalent bond. And so to break that, you're going to have the addition of a reducing agent. So if you see a question that says, somebody got a hold of bleach or you're using beta-mercaptoethanol, whatever, a reducing agent, it's going to be referring to breaking this disulfide bond. Okay, and then that leaves us with our charged amino acids. Again, they're going to say charged, that they have a plus or minus sign. These have ionic bonds, and opposites attract, so a plus is going to bind with a minus, okay? These are moderately strong, and again, pH or salt is going to break them. So when you have a question that says, what would happen if you change a hydrophobic with a hydrophilic amino acid, a polar amino acid, well, it's really going to mess up that tertiary structure because the hydrophobic guys are used to hiding on the inside, and now you're replacing them with somebody that loves to hang around with water. So that's really going to affect how they're folding in that tertiary quaternary structure. Okay, so I hope that this was helpful, and let me know if there's anything else I can help you with. All right, have a great day. Bye-bye.